Okay, first of all, thanks to the organizer for giving an opportunity to present my ongoing work here. So the title of the talk is Periodically Driven Array of Single Rydberg Atoms. This work has been done with my master's student, Sagarika Bessa. She is currently moving to the Rice University for her PhD. So what comes into my mind is like when I say driven, it's like something which is moving forward. Okay, so we can periodically drive the system and to move faster, or we can just transport matter from one place to another. Okay, by periodically driving. So when we come to the physics, it may even slow down. Okay, not necessarily it always go fast, and we can also see some interesting classical and quantum dynamics in systems. So here I will just mainly focus on the array of Rydberg atoms, where at each site you have one single atom. And this atom is coupled from the ground state to excited state by a laser field. And this laser field, the frequency of the laser field, I modulate periodically in time, as I show you. And then we look at the atomic physics or the excitation dynamics or population dynamics of the system. So just going to my system, so I just want to show that this periodic driving can lead to interesting scenarios, even from a classical point of view. For example, if you take this Kapitza pendulum, which is vertically modulating, okay, and then when you could see that typically what you see is the trajectory where the pendulum is making this small amplitude oscillations here, and which is given by this trajectory, the circle here in the center actually. But with this vertical vibration, for instance, you can stabilize the top point of suspension actually. Okay, and this is kind of interesting things. One can see this is in a classical system. So when you come to a quantum mechanical system, the systems, I mean, the scenarios can get more intriguing actually. So, and this is called the dynamical stabilization in these classical systems. And the people have been studying these periodically driven systems extensively in many cases. For instance, one of the first papers which comes was the coherent destruction of tunneling. So you take a double well potential, and by periodically driving this potential, you can localize the wave packet in one of the local sites. Okay? And my studies will also come into some ideas similar to this actually. Instead of the tunneling, we try to suppress the Rabi coupling between the ground state and the Rydberg state. In the same vein, actually, in the localization of wave packet in one of the well, it is identical to the population trapping in one of the atomic states. Okay. And another interesting thing is like you can sit in a Lando's inner transition point and then do this periodic modulation, and you can see something called a Lando's inner Stuckelberg interference, where the different Lando's inner transitions interfere constructively or destructively. Okay. And recently, the attention has been mainly on these driven quantum spin systems, and also mostly in the direction of this many-body localization and so on. And there are a lot of interesting things happening in this direction. Okay. And one of the review you can see here, and Tolly is here also. So you can, this is one of the nice review you can read about all these introduction to this periodically driven systems. Okay. And it's also a general platform to study non-equilibrium physics. So let's come back to my system. My setup is called the Rydberg atoms. So what are Rydberg atoms? I just give you a short review. So these are the atoms in which the valence electron, typically we take alkali atoms. The valence electron is excited to very high Rydberg state. So these atoms are very huge in size actually. And the key point, which is if I take these two Rydberg atoms, they interact with a dipole-dipole interaction. And very far distances, this interaction can be written as a van der Waals interaction, which scales like n power 11. So that means if I go to a very large Rydberg state, this interaction is tremendous actually. It's very huge interactions. So we can explore the properties of these interactions in Rydberg states. So that's why the Rydberg atoms are getting a lot of attention because of these huge interactions. And if you can modify this interaction by putting an external electric field or something, you can make it dipole. Okay. And the other property is that the interaction is highly tunable. So you can tune this, and you can also change the interaction strength by changing the separation between the atoms, and which is easily doable, for example, in an optical lattice and so on. And the interaction is highly anisotropic because the kind of interaction between the two Rydberg atoms depends on the particular Rydberg state you choose. For example, if you choose S state, which is radially isotropic, you can get an isotropic interaction. If I can choose P state or D states and so on, you get highly anisotropic interaction. So the remarkable properties are it's a composite object. You can see that this is a core here, and the valence electron is doing some dance here actually. And then there is, it's like a mesoscopic. This object can be order of micrometers in size actually. And as you go higher in the Rydberg state, the lifetime is huge. So that gives us enough time to probe and do some dynamics or something with these Rydberg atoms. And highly susceptible to external field, obviously, due to the polarizability. The decay rate will be, it will get narrower and narrower, the energy levels. So recently, the interaction between these Rydberg atoms has been measured, and you can see that over a range of micrometer, this is order of megahertz, it's 10 megahertz, and these are huge interactions when we speak about ultra cold atoms and so on, okay? And this means you can see fast dynamics in the system. And this has been recently shown actually, experiment. These are the experimental results and the theoretical calculated using the perturbation theory. So there is a celebrated property of Rydberg atoms, which is called the Rydberg blockade. And this has a huge, I mean, there are many applications associated with this Rydberg blockade. And I just explain what is the Rydberg blockade here. And I will show how the Rydberg blockade get modified or what happens when I periodically drive the system. So in order to explain Rydberg blockade, so we take two atoms and then we go to this basis GG, RG and GR. And this is the two atoms in the Rydberg state. And when the atoms are in the Rydberg state, they interact. So that means that there is an energy level shift due to the Rydberg interaction here. Okay? And these are the two levels here. And the Rydberg, two atoms in the Rydberg state, there is a level shift due to the Rydberg interaction, which is a van der Waals interaction, which falls off like 1 upon r bar 6, where r is the distance between here. So if here I'm able to excite the two atoms to the Rydberg state at these separations, okay? But if I come closer, if these two atoms, if the two atoms come closer, and due to this huge level shift, due to the Rydberg interaction, these double excitation states are not possible, okay? And this is called the Rydberg blockade. So within a radius, I cannot excite these two atoms simultaneously. And I can define something called the blockade radius. Here, it's shown here. And then what happens is the system will make a Rabi oscillation between the ground state and a coherent superposition of all the single excited states. This is a collective single excitation state here. Because you cannot have more than two excitations if the system is fully blockaded in this region. So if I take a collection of atoms, it is fully blockaded. What happens is like the physics can be reduced to a two-level system, where the two levels are the fully ground state here, the many-body ground state here, and the collective single excitation here. So that means the people call it as a superatom because all the ensemble of atoms are just reduced to a two-level atom. Okay? And this is called the superatom. And this has been experimentally shown. For example, here the red curve shows a Rabi oscillation in a single atom in the absence of any atom, okay? And in the presence of the single atom, in the second atom, and due to the Rydberg blockade, there is an enhancement in the Rabi frequency. Typically, it is root n times the Rabi frequency. So you can see that in the presence of the second atom, the Rabi frequency has been enhanced. And this has been shown as the proof of the Rydberg blockade, actually. Okay? So here it is 2 atoms actually. The experiment is done with 2 atoms. So you take 2 dipole trap and you. So I just writing a general case actually. So in this case, the experiment is done with 2 atoms. Which one? Exactly. So it scales as root n actually. No, actually this experiment has a spontaneous emission. The dissipation is here. That's why you can see kind of exponential decay here actually. Okay. So the experiment has the spontaneous emission actually. The temperature is you can treat like a 0 temperature. Right? So coming back to my setup, so what I consider is like a 1D lattice with 1 atom per side, and each atom is coupled to a Rydberg state, and I assume that the detuning is time dependent, which is oscillating with the amplitude small delta, and omega 0 is the oscillation frequency. And this setup is realistic now, okay? These 1D chains are realistic, and even the 2-dimensional array of atoms are also recently been shown for realizing quantumizing models. And there are many recent works which show that you can achieve these systems in experiments. So I'm not going to the details of these things actually, but to show that the setup we consider is more realistic actually. So it's possible to get this 1D kind of chains actually. So coming back to this, so the system is described by now, the following Hamiltonian. So the first term is coming from the detuning here, and the second term is coming from the Rabi coupling between the G and the excited state, basically the Rydberg state. And the last term is the Rydberg interaction if the 2 atoms occupy the excited state. So in order to see what happens from to get an intuitive picture actually, especially at high frequency driving, we can go to a rotating frame. I didn't write in details, and you can write effectively this Hamiltonian in this form. Okay. So what happened is, by engineering, I can engineer the Rabi couplings. Now there is a time dependent here, and the Rabi coupling is also modified by a factor of depending on the Bessel functions, okay, and which in turn depends on the modulation parameters like the amplitude and the frequency of modulation. So what we do is, by modulating the Rabi, the detuning, or by introducing the periodic dependence in a detuning, I'm effectively modifying the Rabi couplings actually. And this is the physics behind whatever I will show later actually. Okay. Okay, this is just, you can write in terms of polymetries also. So this will be just 0, 1, 0, 0. Yeah, so in the EG basis, you get 0, 1, 0, 0. So the key idea here is you engineer the Rabi couplings by periodically modulating the detuning. So let's consider a single atom, and I define different regimes where of modulation parameters, and then we will see what happens if I put more atoms here. For a single atom, the Hamiltonian is very simple. There is no interaction, so this is just the detuning and the Rabi frequency. And what really happens in this dynamics, I mean by dynamics is how the population in the excited state and the ground state evolve in time. And it depends on this modulation parameters, the small delta and the modulation frequency. The most simple regime is the adiabatic regime. It instantaneously follows the ground state. And if the amplitude of modulation is much smaller than this omega effective, which we call as a weak driving limit, okay, and you have a resonance, and which is omega effective, if you diagonalize the full Hamiltonian here, and the energy separation between the 2 states will be omega effective. So you can treat this case as a simple periodic perturbation, and the frequency of this periodic perturbation matches the energy separation between the 2 states, you get a resonance. So that means if I start in the ground state of the atom, I can drive resonantly the transition between G and E if I satisfy this condition in this weak driving limit. Okay? So you have a resonant transition between the G and the E state. And now I go to the high frequency limit where the periodic modulation is the frequency is very high actually. So in order to understand, I take the single atom Hamiltonian, so which I shown before. I've written in terms of the Bessel function, okay? And you can see that these terms are oscillating very fast, and the only contribution which comes is m omega 0 minus delta 0 equal to 0. So that gives me the resonance condition, okay? If this satisfies, I have some contribution from here, okay? And in the high frequency limit, these are the resonance condition for the transition between G and E. And the Rabi oscillation frequency, you can see that this will come out, and this will be just given by this for a particular n which satisfies this condition. Okay. And this n can be chosen by choosing the offset which you initially take in the detour. For instance, if you take delta 0 equal to 0, then I will get a Rabi frequency which is omega prime is equal to omega times the J0 of this parameter. So this is a thing actually. So if delta 0 equal to 0, I said that the Rabi frequency between the G and E is given by this function. So that means if I can choose this amplitude of oscillation and the frequency of oscillation such that this Bessel, you are at the Bessel root, so that means there is no dynamics at all. So that indicates the population trapping actually. So where you start, you will be there actually. So you can make this root of the Bessel function give you the population trapping, and this is identical to the suppression of tunneling in a periodic lattice. Okay, and this has been also studied using BEC in a shaken optical lattice, and in fact you can see that this is the amplitude of the modulation. For a fixed frequency, you can see that you can get this, the hopping between the site 0. You can completely suppress the hopping between the site by periodically shaking the optical lattice in a piece. Okay. And which is identical to suppressing our Rabi frequency in a two-level system by periodically driving the detour. And there is another limit which is called the fast passage limit. So you have a Landau-Zener transition point here, and around this point we move very fast. So that means around this point, if I can expand in time, I can write the Hamiltonian in this form. This is the typical Landau-Zener Hamiltonian. And you can write down in terms of the velocity across at which you are modulating. This is the delta, okay? This is the delta. You are moving across this Landau-Zener transition point. And then you can calculate, I mean, I'm not showing the details here, so then you can show that the resonance condition is given by this, okay? And at this transition point, you have a non-adiabatic population transfer, and away from this Landau-Zener transition point, you have an adiabatic regime where you just acquire some phase actually for these two states. So in short, I want to summarize that. So if for sufficiently large value of delta, this the fast passage limit and overlaps with the high frequency limit. So in summarizing, so I have three regimes. One is the weak driving limit, where the amplitude of modulation is very small compared to the effective Rabi frequency. And there is a high frequency limit, and this expansion in terms of the Bessel function is very useful. And you have another limit which is called the fast passage limit. You use it as a Landau-Zener transition point, and you just modulate very fast. And in these last two cases, the resonance condition is given by a given condition, same condition. Okay. And the first case, the modulation can be treated like a periodic perturbation, and this resonance condition is just given by the energy level separation between the states. And now what I will do is, I will go to two atoms. So now we will look at what is the role of interactions actually. So we have two atoms. Each one is coupled to a manifold or Rydberg state. I mean, even though it's shown like a dense states here, we can choose a particular Rydberg state experimentally. Okay, it's not a difficult. So I'm looking for two resonance transitions. One is I start all the atoms in the ground state, so I have a GG state here. So I look at the transition from GG to plus state, and this I call as S resonance. S means a single excitation. You can see that the state is a superposition of singly excited states. And as shown before, this corresponds to the blockade dynamics if there is no population in the doubly excited state. okay? And this S resonance correspond to the blockade dynamics if there is no population in the double excited states. And the second resonance, I call it as D resonance. D means that there is a doubly excited state, okay? So we look at these resonances in this system. So first look at the weak driving limit. So one way to look at the resonances is I calculate the average, time average population in all the three states and plot. And the dips and the peaks in this population will give me the resonance conditions. Okay, these are the resonances. So I start with both atoms in the ground state, and this is a modulation frequency. And I sweep through this frequency, I see that there is a transfer of population to either plus or E state, and these peaks will give me the resonance conditions, the resonances. And the S is here actually, and the D is here actually. Okay. And this blue dashed line represents the population in a doubly excited state. So just forget about all the details here. The one interesting thing we see here is this guy. So the GG population is transferred to the plus state, and there is a negligible population in the doubly excited state. And this is basically the blockade dynamics. And even we see this blockade dynamics, very small interactions. Typically, you need the interaction to be greater than the Rabi frequency in order to see the blockade. But the key thing here is the periodic driving leads to a blockade enhancement. Even there is a small interaction, you can see a blockade. Okay, this you can see it here actually. So it will be more apparent later in the high frequency of fast passage limit. And that means even, the interaction strength I can change by changing the separation between the atoms. So that means even the atoms are very sufficiently far apart, I can create some entangled states, which is a plus state, okay? So that means I can create the blockade even they are very sufficiently far apart by periodically driving the system, okay? So periodically driving the detuning, and this is very remarkable. So you can calculate the resonance frequency. So for small interactions here in this regime, I can treat the two atoms to be non-interacting, and the interaction can be taken into account through effective detuning. And this dashed line and the solid line represents the analytical results, and this bubbles represent the numerical calculations. And this non-interacting picture matches very well in this regime, but at some point it violates, and you have to really take into account the interaction. You cannot write the non-interacting picture anymore. So this we just span the resonance frequency as a function of the interaction strength. And there are two regimes. I cannot well define this resonances because when V0 is equal to delta 0, okay, these are just giving the analytical results which obtained by the perturbation theory. I don't go in details here actually. So this agreement very well with the numerical calculations. So around V0 is equal to delta 0, I get plus and E are almost degenerate. So I cannot really resonantly drive from GG to plus or E because you will populate both the states. So there is no meaning to talk about the S and D resonances separately. And similarly at this point, both GG and E are almost degenerate. So that means even in the absence of driving, I get the D resonance, okay? But it's not the case for the S resonance actually. This indicates the resonance frequency is coming to 0. So let me look at the high frequency limit for two atoms. And in order to just get an idea, I can introduce following the unitary operator. And effectively then my Hamiltonian will reduce to two off couplings actually. This correspond to omega 1, which correspond to GG coupled to plus state and the plus state coupled to E. So my Hamiltonian reduced to these two terms. These are the only matrix elements in the Hamiltonian. And you can see that this is which is called the S resonance, is possible when this time dependent part in this exponential is 0. This gives me the resonance condition. This is N2, sorry, this V0 is not there actually. So N2 minus delta 0 equal to 0. This is N0, this is S resonance, and this corresponds to the oscillation between the plus and EE state. These are the two conditions which I get from these two Rabi couplings in the Hamilton. Okay. Yeah, so I just use a continuous wave and which will drive both atoms. This we haven't looked at it. Okay. So then that means you have to address the atoms locally, which will be more difficult than doing it globally. What? No, it is so I am considering from the GG. So everything initially the atoms are started from GG. So the minus state is decoupled from this. Yeah. So if both resonance conditions are to be met simultaneously, then it is very clear that this N1 has to be not equal to N2. And in that case, I can have a resonant transition from GG to the EE state actually. Okay. So if you separately satisfy the resonance conditions, and you can suppress one of the transitions actually. So if the first resonance is satisfied, you can suppress the second transition, and similarly the otherwise actually. So that means here I have a state dependent population trapping. So this I'm not going to the detail here. So let's take the two resonance conditions are satisfied. So all the oscillation, the modulation frequency and everything is fixed by this resonance condition. So the only free parameter is here is the amplitude of the modulation. So that means I can see through the dynamics as a function of delta, and I can see various dynamical scenarios. For example, small delta, you still have I'm taking a case in which these two atoms are fully blockade. So you have a resonant transitions between the GG state and the plus state. And for small amplitude of modulation, this is preserved. But there is a particular delta, you can have a population trapping, so you will start where you start, you will be there actually. So if these two resonance conditions are satisfied, you can use this modulation amplitude as a single parameter to tune your system from various dynamics actually, okay? So this I can just say that this is can be used as a prop to see through all these parameters. So this is the population trapping we have been showing. So in the fast passage limit, I said that before we can study this problem using a Landau-Sinner transition. But now if I increase the number of atoms, the number of Landau-Sinner transition points also increases. For example, if I take the two atom case with the three basis states, you have the three Landau-Sinner transition points, and this makes the analysis much more complicated actually. So the tricky thing here is you can increase the interaction such that these Landau-Sinner transitions separate very far apart. And then you can clearly define the adiabatic and non-adiabatic regimes. And then you can do all this calculation and obtain the resonance conditions. Okay? So in that case, I'm not showing the calculation details. So you can construct the matrices which correspond to the non-adiabatic transitions across each of these Landau-Sinner transitions. And there are these white regimes which define the adiabatic regimes where you occur a phase. And then in principle, you can calculate all the resonant transitions or the resonant conditions for this. And you can clearly see that the resonance conditions inevitably depends on the interactions. If these interactions are 0, then you see that all this gets overlapped and you get all the populations. But you can choose the interaction, you can control the dynamics in this system. So the key point here is, so the interaction between the atoms and also the modulation frequencies and so on, we can control the population dynamics in these driven periodic Rydberg systems. Okay? For instance, so it's everything can be summarized in this plot actually. Okay? So this thin line, which what we are plotting here is the population in the doubly excited state of, as a function of the V0 by omega, which is the interaction strength. So the doubly excited population is averaged over a long time. And this thin line shows the case without any periodic driving, and you get the decay of population indicating the dipole blockade. Okay, it's a complete blockade of the doubly excited state. And the thick line show in the example of a driven case, and you can see that the P drops off very fast in this, even in this small interaction regime, indicate the enhancement of the blockade. Okay, and this indicates the blockade enhancement. And contrary to the non-driven case that you don't see any doubly excited state at large interactions because of the Rydberg blockade, here the resonance conditions give you the population in the doubly excited state, which is called the anti-blockade. So you populate the doubly excited state, okay? No, here I am sweeping through the V0. So, okay, if you fix the separation between the atoms, the way to increase the interaction is to go to a higher Rydberg state. No, here I just change the V0. If there are two atoms, you can change the position or you can change the strength of the interaction, which can be done by changing the atomic state. The effective interaction is small actually, it doesn't matter, two atoms, right? So I solve the Schrodinger equation. I start with GG and then evolve for a long time and then integrate over the, exactly. It's a long time out. So you can see that because of the resonance conditions, you keep getting the anti-blockades actually, okay? So you can get the doubly excited state even at very large interactions. So these are without including the spontaneous emission. So the people will ask us, so take a real system. So we took a rubidium atoms and took the 45s half state and included the spontaneous emission, okay? So then you can see that you can still see the blockade enhancement. If I choose all these parameters as it is not difficult things to do in the experiment, okay? And the interaction is half the Rabi frequency, and this you can easily tune because it depends on where you keep your atoms. And now with optical tweezers and so on, you can just fix the two atoms wherever you want actually. You can just move, you can play around. So that means, in fact, you can see the blockade enhancement. For example, if I take 45s half in a rubidium atoms, okay? So this is highly realistic actually to show in a current experiment. So if I increase the number of atoms, more resonance will come into play, and this will complicate the things actually. And you see that in order to isolate each of these resonance, and if you want to control the dynamics of your atomic system, you need sufficiently strong interactions, okay? The one resonance which is independent of the interaction is the coupling between the fully ground state and the fully, the collective single excitation state, okay? So that is independent of the interaction, which you can imagine. And all other resonance depends on the interaction strength. The key is like, if you can probe these resonances, you can get all these dynamics in your systems actually. This will have some consequences, for example, in preparing the crystals, the Rydberg crystals or something like that. So I can choose a configuration which I want to prepare. For example, I can control through these resonances actually. So the last part, which is some ongoing work actually, so I want to show that a dynamic application of this periodic driving as a dynamical localization of a many-body configuration. What we do is we start with one single excitation at the center of the lattice, and then we introduce this periodic driving and so on, and we carefully choose the parameters. I'm not going to details. So what we look at this parameter, which PA is the probability of finding any other eigenstate, okay? And we look at this parameter and see what happens to this initial state in the presence of a periodic driving. So in order to see the effect of periodic driving, first we look at this dashed line, which is for 15 atoms, okay? This is a full atom dynamics actually. For small atoms, without driving, this is the undriven case, you can see that if I start with this state, it will just collapse, and then there is a revival because of the finite size of the Hilbert space. But if you increase the number of atoms, the Hilbert space grows exponentially, and this revival is not there actually, okay, because of the large number of Hilbert states in the Hilbert space. So you can see that there is a rapid collapse of the initial configuration which I prepared, okay, because this state is coupled to other state through the Rabi couplings, and this just distributed over all the states in the Hilbert space. But now with periodic driving, which is this curve which is showing here, and this oscillation is due to the Landau-Sinner oscillations actually. And this you can see that I can hold this state even longer. I can stabilize this state even longer actually. So for a particular example is shown here, the decay of this state is as an exponential behavior. This is like a Gaussian behavior actually. So what I do is I calculate the width of this Gaussian, which gives roughly the time of this dynamical localization. And I probe as a function of the interaction. So I will see that how the interaction plays a role. So what we found is like, yeah, interaction indeed plays a role for the dynamical localization of this particular many-body configuration. And there is a particular interaction strength. This time diverges actually. Okay, so we are in this fast passage limit. We've taken sufficiently large frequency and so on. The details I'm just skipping. So you can see that I can localize this for a long time in this particular interaction strength. So we are just exploring this. So this is V0 by omega is equal to pi. This will be around here. So this is a histogram showing only the singly excited state, which found that for a long, for the small time, duration of time, the system is trapped in this reduced Hilbert space of singly excited states. Actually, there is no transition to doubly excited or triply excited states. Actually. Eventually, it will populate all other excited states, but in a small duration of time, it is trapped in the singly excited state, which will give you the histogram here. Actually, this is a 15 state for 15 atoms, and exactly at this localization point, you can see that almost all the population is trapped in the middle side, and this shows a time average population. This is we average over a long time duration. Okay. And this work is in progress actually. So with this, I will conclude my talk. I just want to say that the periodic modulation of the driving field leads to interesting scenarios in Rydberg atom dynamics. For instance, you can have blockade enhancement, and you can also have anti-blockades at large interactions, which is unexpected. And you can also have a dynamical localization of a many-body configuration as an application for this driven system. And thank you all for attention.
Okay, so the talk is open for questions.
So in the two-atom case, at least, I'm not sure about the others, couldn't you just have two driving fields with different frequencies and do the same kinds of physics? Yeah.
So you're saying that the two atoms are driving at two different frequencies, right?
Well, the two atoms together, driven with two different frequencies, and they're different because one of the transitions will have a different frequency because of the blockade effect.
You're taking the two atoms and driving with two different frequencies,
yeah.
Right?
So one of the frequencies would be resonant, let's say, with GG to
state
plus, and then the other field would be resonant with plus to EE. Does that work?
I would say, I mean, I cannot say exactly, but it also depends on the amplitude of the modulation.
In your case, yeah.
Yeah.
Because of the Bessel function.
I cannot easily say what would.
So this was all done with open boundary conditions, right?
Yeah, exactly.
So how would it change if you had periodic boundary conditions, or like if you considered some kind of thing? So how sensitive is this physics to what's the...
So this will mimic the infinite system, right?
So I'm just curious, like if you had a ring or something.
I haven't tried actually. So probably it may affect this localization behavior. Mm-hmm. This is what I can comment actually.